Welcome back to Codex. Our speaker today is Tamir Bendory from Tel Aviv University. Professor Bendory is an expert in the mathematics of data science. Today, he'll tell us about unitary matrix retrieval. Take it away, Tamir.
Okay, thank you very much, and thanks for the introduction. So the talk, it has three main sections. I'll start by introducing the problem of estimation of the groups. Then the main part is going to be the second part of the second moment analysis and the role of semi-algebraic priors. And if time permits, I'm also going to say a few words about algorithms and specifically about a new family of algorithms that we have designed for these problems. So 1 second, how do I hide? No, sorry. So this is on YouTube, huh? Okay, good. Okay, so the problem that I'm considering, it's typically it's called multi-reference alignment, or MRA, where we have a group G acting on a vector space V, and we want to estimate a signal or a vector F in the vector space from n observations. The observations are the Y's. And each observation F, the signal is acted upon by some random group elements, the GIs. And we have some noise, some Gaussian noise. These are the epsilon. So the goal is to estimate F from n observations. However, we don't know the signal or the vector F, and we also don't know the group elements. Although we don't know both of them, we only want to estimate the signal F. And we treat the unknown group elements as nuisance variables. So we don't know them, but the goal is not to estimate them. In addition, since we don't know the signal F and the group elements, generally the best we can do is to recover F up to a group action, or more technically, to recover the G orbit of F. And this is what we are trying to do. So now I want to give you two concrete examples of this model that we're going to use as the running examples throughout the talk. So the first example is the 1D case, the 1D MRA case, where the vector space is Rn, so we're talking about just signals with n elements, and the group is Zn that acts by circular shifts. So here you can see examples. So in the left column, the three measurements with no noise. So basically, these are three copies of the signal, each translated by some different translation. And here the problem is trivial because each observation is a solution, because the solution is up to a group action. In the middle column in red, you see the problem in the highest NR regime. So we do have some noise, but still the signal dominates the noise. So you can imagine that perhaps you can try to estimate the relative shift, undo the group action, and just average out the noise. This seems to be quite simple. The problem becomes more interesting on the right column here, where the noise dominates the signal. The SNR is quite low. And the question is whether we can still estimate the signal in this regime. And if so, how many samples do we need? What's the sample complexity of the problem? And how we can do that? What algorithms can we use in order to estimate the signal? So that's the first example. The second example, it arises from a technology called single particle cryo-electron microscopy, or cryo-EM, which is a very important technology to reconstruct the 3D structure of molecules such as proteins. So in the experiment, they take many samples of the molecule. This should be the molecules, and they freeze it in a very thin layer of ice. Okay, this should be the ice. Now they take the ice with the embedded molecules, they put it in the microscope that transmits electrons from one side, and we measure the tomographic projection on the other side. Tomographic projection is just the line integral, the 1D integral along the z direction, and we get these shadows, these 2D projections. We can model each observation as my 3D structure F. This is what I want to estimate. After it has been rotated by some unknown rotation, this corresponds to the unknown orientation of the molecules in the ice, and we treat them as random elements of SO3. Then we have the tomographic projection and noise. And the goal is to estimate the structure F from n observations where the 3D rotations are run onto us. And also the SNR is very, very low. So I want to give you an example. So here you can see 4 typical experimental images. And as you can see, you can barely see the projection or the information below the noise. So this is one more reason we are going to focus on the lowest NR regime. One more comment about cryo-EM is that It's not precisely the MRA model that I showed you before because of the projection. So this is the projection is a linear operator, but it's not a group action. However, from the perspective of this specific talk, we can ignore the projection, just treat this problem as a 3D structure acted upon by random SO3 actions. And I'll explain later on why it makes sense to ignore the projection, again, just from the perspective of this talk. So I showed you two examples, the 1D case and the cryo-EM case, but the results that I'm going to show you are actually very general, and they hold for many different MRA cases. Here is a partial list of different MRA cases that have been studied in the literature. I'm not going to go through them, and I'm going to focus on these two examples, but I do want to emphasize that the results are general, and they remain true for many different MRA models that were studied in the literature. So this is the introduction. Is that clear? I want to make sure that the model is clear before I'm going into the problem and the models and the specific analysis that I want to show you today. Any questions before? Okay. So 1 second. It gets hot here. Okay, so now we're going to start the analysis. I'm going to focus on the second moment and try to motivate why do we care so much about the second moment. So first of all, usually when we think about the MRA problem, we think about two regimes, the lowest NR regime versus the highest NR regime. So just to remind you, we want to recover signal F in the vector space from n observations, the y1 to yn, where each observation F is acted upon by a random group element and noise. The first insight, which is very simple, is that if the group elements are known, then the problem is very simple. You can undo the group action, undo the translations or undo the rotations, and just average out the noise. That's very simple. And this simple observation motivated many works about trying to estimate the group elements from the observations. For example, a very effective framework, it's called group synchronization, where basically you're trying to estimate, first of all, trying to estimate the pairwise ratio between the group elements from the observations, and then to estimate the group elements from the pairwise ratios. So basically, that's what you're going to do if the SNR is good enough and you can actually estimate the group elements. However, in the lowest NR regime, which is the regime that we're going to focus on, it's actually impossible to estimate the group elements. It's impossible to, for example, in cryo-EM, it's going to be impossible to estimate the rotations or impossible to estimate the translations and so on. So before I show you some results, I want to show you one figure taken from one of the papers. It's a result of a numerical experiment. The specific details of the experiment are not very important for the message that I want to convey. But it's an algorithm that we employed. The x-axis is the noise level in the experiment, and the y is the error. And you can see that if the noise is low, the highest NR regime, the slope in the figure is 1, meaning that the error is proportional to the standard deviation of the noise, which is what we used to see in many different estimation and signal processing problems. That's not surprising. However, in the lowest NR regime, we can see that, first of all, we can still estimate the signal. Although the SNR is very low and seems very challenging to estimate the group elements, the rotation and translations, it seems that we can still estimate the signal, but the estimation rate, this curve becomes very steep, and we get a slope of 3 here. And that's something that we want to understand. First of all, whether we can estimate the signal, and why do we get slope of 3 here? So that's something that currently we understand, and I want to show you why do we get this result. So now I'm going to focus on the lowest NR regime, and specifically I'm taking the noise level sigma to infinity, and also the number of observations. And as I said, in this regime, we cannot estimate the group elements anymore. We cannot estimate the rotations or translations. However, in many cases, we can still estimate the signal itself. For example, in cryo-EM, even if the SNR is very low, if we have enough observations, we may be able to still estimate the signal, the 3D structure of the protein, although we cannot estimate the rotations associated with the different samples. And to be more precise, we understand the sample complexity of the problem. So we have a parameter D, which is the lowest degree moment of the observations that determine the signal uniquely, or the orbit of the signal uniquely. And then the number of samples that we need to acquire, n, should be much greater than sigma to the power of 2d. And this is true regardless of any specific algorithm that we're going to use. So, for example, we already know that this sentence summarizes something like, I don't know, 5 papers, but generally we know that for many different MRI setups, for almost all signals, D is equal to 3. It means that we cannot recover the signal from the first or the second moment, but we can recover the signal from the third moment. And this means that N, the number of observations, should be much greater than sigma. And again, this is true. It's not a question, right?
You guys can force him to mute, I think. Go.
Okay, good.
He's been muted.
Feel free to ask me questions if you want. Anyway, so D is equal to 3, meaning that N should be much greater than sigma to the 6, and this is true regardless of any specific algorithm. And today, I want to explore with you the possibility to recover the signal from the second moment, not from the third, but from the second moment, or to identify classes of signals that can be recovered from the second moment. And why do we focus on the second moment? First of all, in order to estimate the second moment, we need only sigma to the 4 observations, and the sample complexity will be proportional to sigma to the 4 and not sigma to the 6. So we need fewer observations. From the computational perspective, the dimensionality is lower because the dimensionality of the second moment is quadratic in the dimensionality of the signal, whereas third moment is cubic. We have very good tools to estimate the second moment in practice, especially in high dimension, based on statistical tools like the spike model, and different techniques. And in addition, that's something I want to show you in a few minutes. The second moment analysis also provides us a unified analysis that connects a complete problem that seems completely unrelated, like cryo-EM and the crystallographic phase retrieval. We're going to treat them together in a one framework, both analysis framework and computational framework. Okay, so I want to start the mathematical analysis. This part is based on the joint work with Dan Edidin. So again, this is the model. F, the signal you want to recover, acted upon by random group element G, and we have Gaussian noise, and we get the observations Y, and we assume the distribution, here we assume that the distribution over the group is uniform in this case, and from here to for the rest of the talk. So we're going to study the second moment, which is the expectation of YY star, which is given by this integral, and it can be approximated from the data just by the empirical second moment. And we know that if n is much greater than sigma to the 4, then by the law of large numbers, basically the empirical second moment will converge almost surely to the population second moment. So that's what we're going to assume. Assume that we have enough observations, sigma to the 4 observations, and we have this population second moment, and we'll try to identify classes of signals that can be recovered from the second moment. So we're going to do it in basically 2 stages. So the first stage is to try to we try to understand the algebraic structure of the second moment. It has a very unique algebraic structure that we'll see in a few minutes. And then we'll see how we can use the second part will be to see how we can use semi-algebraic pliers to identify this class of signals that can be recovered from the second moment. So I just want to remind you 2 basic notions in group theory. The first is a group representation, where I'm going to refer to vectors V equipped with the action of G as the representation of G. And for example, in the 2 examples that I'm going to consider, in the 1D MRI case, just to remind you, G is the group of Zn and V is the group Cn or is the representation Cn or Rn. And in cryo-EM, G is going to be SO3, the group of 3D rotations, and V is going to be L2 functions over R3. And for us, it's very important that the representation, the ternary representation of a compact group, we can represent each element as basically as a multiplication by a unitary matrix. The second notion is irreducible representations, where the definitions that a representation is irreducible if it has non-zero proper G-invariant subspaces. But for me, it's easier to think about it that the representation is reducible if it's equivalent to direct sum of other representations. So basically, these are the basic building blocks of the representation. And another thing that we're going to use many times is that any finite dimensional representation of a compact group is decomposed into a direct sum of irreducible representations. Okay, now we can start. So we're going to start to analyze the second moment of this model, the algebraic structure, and we're going to do it in 3 stages. We're going to start from the simplest case, and then we're going to treat more and more general cases. This part is going to be a bit technical, but afterwards I give concrete examples, so I hope it's going to be clear. So at the first stage, we're going to assume that V is irreducible. And in this case, we're going to see in a minute that the second moment gives very little information about the vector F. And to this end, we need to understand basically 2 things. First of all, that the second moment is invariant under the group G, because the second moment of F and GF is the same. We get the same second moments because basically the second moment is at the integral over the group. The second key is that we think about the second moment as a linear transformation. In this case, it's going to be G-invariant linear transformation from V to V. And now we can invoke Schur's lemma that tells us basically that since V is irreducible, then the second moment has to be a scalar multiple of the identity. So this is the first result. We let V to be an n-dimensional irreducible representation of some compact group, and we identify V with Cn by choosing some orthonormal basis. Then the second moment map from Cn to Cn squared is just the map between F to the norm squared of F times the identity. This means the second moment basically gives us the one number, which is the norm of F. So it's not very useful in this case, where V is just an irreducible. So that was the first. The second step is a bit more complicated. Now we consider we have V0, which is an irreducible, and V is going to be direct sum of R times V0. So V is not irreducible, but it's direct sum of it's R copies of some irreducible V0. This means that if we have a vector F in V, we can always decompose it as this sum F1 up to Fr, where each component here is in a copy of the irreducible V0. So this discussion or this case is mainly motivated by cryo-EM. So in cryo-EM we have R3, but we have L2 function over R3, but we're going to discretize R3 as multiple copies or multiple shells. So basically we have SO3 acting on our copies of L2 functions over the sphere. And I'll try to explain it in more detail later on. But this is the main motivation why we consider this representation. So basically, using the same reasoning that I showed you before, if we view F, the signal F, as an R tuple from F1 to Fr, each one of them is in the irreducible V0, from the second moment, we just get the inner product between Fi and Fj. That's the information we get from the second moment, and it's more convenient to reorganize the signal as a matrix F, where it has R columns, which are the different elements, F1 to Fr. So we want to recover or want to identify this matrix F, but since we get the inner products, what we actually get is the F star F. So we want F, but from the second moment we get F star F. Or put it differently, the second moment determines the signal f up to symmetry or ambiguity of a unitary group of dimension n0, where n0 is the dimension of v0. So this is the second step, and now we can consider the third step, which is the more general case. Now we have a finite dimensional representation of this form, V, which is a direct sum of k distinct irreducibles. Each one of them may appear rk times. So this is the most general situation that we're going to consider. And this means that we can write any vector or signal f in V as follows, as this sum over the k's and the i's, where fki is going to be in the ith copy of the kth irreducible. And now we're going to use, again, Schur's lemma. So Schur's lemma tells us that any G invariant linear transformation of the group G is either 0 or an isomorphism. In our case, since VM and VK are non-isomorphic by definition, it means that all the interaction between the elements in the different representation has to be 0. That's basically what it implies. And this in turn implies that what we get from the second moment is these inner products, the FKI, FKJ, where I and J goes from 1 to R. So these are the different copies. But importantly, it's the same case. So again, there is no interaction between the different irreducible. If again, we reorganize F as a set of matrices, Fk, where Fk goes from 1 to K, these are, again, the different irreducibles. So we want this set of matrices, this Fk. That's the information that we want. But what we actually get is Fk star Fk. So that's what we have. We have this inner product, and this is what we want. This is the signal that we want to recover. So basically, this is the main result stated here. So I'll state it, and then we're going to see some concrete examples that will help us to understand. So basically, the main result is that if decomposes as a sum of irreducibles of this form, then the vector f is determined from the second moment up to the action of this ambiguity group, which is a product of unitary matrices with the appropriate dimension. Okay. So let's see two examples. I hope it's going to make everything very concrete. So the first example is the 1D case. So to remind you, in this case, the group G of Zn, the group Zn acts on Cn or Rn by cyclic shifts. And we know, I know from basic signal processing, that in Fourier domain, we can think about this action as multiplication by roots of unity as follows. So basically, if f here is the signal in Fourier domain, then this is basically the action where omega is the root of unity. So that's the action of G. Now we also know that Cn decomposes as a sum of these n one-dimensional irreducibles. And now we can directly invoke the results from before that tells that the second moment is nothing but the Fourier magnitudes in Fourier space. This is called the Fourier magnitudes. So that's what we get. In signal processing terms or in physics, it's called the power spectrum of the signal. So the second moment here is equivalent to the power spectrum of the signal. And now, which in turn determine the vector f up to the action of up to n unitary matrices, which again, in signal processing, these are n Fourier phases. That's how we're going to call them. And recovering these n Fourier phases is actually a very important problem in crystallography and optical imaging. In signal processing, it's called the phase retrieval problem, and it appears in many different problems, especially in physics. So that's the first example. The second example is about cryo-EM. It's a bit more interesting. So now we have L2 functions over R3, on R3, and we're going to approximate it or to discretize it using this representation. So basically here we have VK is the n(k+1) dimensional irreducible representation of SO3. This corresponds to harmonic polynomials. And we have R copies of each one of them. So basically, you can think about it as we take concentric shells, and each shell, the function or the signal is L2 function which is k band limited. So if you want to give it to make it more concrete, it can be expanded by spherical harmonics up to degree k. So that's how we discretize. That's how we think about this function over the sphere, and this is actually a very popular model in cryo-EM. So that's actually something that people use in practice, this kind of model. Okay, so now we take F in V. Again, this is F in this case going to be, for example, a protein structure, and we consider it, we view it as an R tuple, F1 to FR, which each one of them is an L2 function over the sphere, which is k band limited. And this means that we can expand the protein structures as follows, where here the YKM are the spherical harmonics and the FKM are the spherical harmonic coefficients. So basically, this means that this implies that instead of recovering the signal F, we actually want to recover the spherical harmonic coefficients, the FKMR. So that's what we're going to do. Now, in order to invoke the result from before, we need to do one more step, which is, because in cryo-EM we do have the tomographic projection, but there is a result that's not very intuitive, but it's true, that the tomographic projection doesn't change, or we don't lose information because of the tomographic projection when we consider the second moment. It's not true in general, because in general, obviously, we do lose information because of the tomographic projection, but the second moment remains more or less the same. So we don't lose information. Let's say the second moment remains the same. So we can just ignore the tomographic projection. We can think about cryo-EM, again, for second moment analysis, as SO3 acting on L2 functions over R3. And therefore, we can invoke directly the theoretical result that I showed you before. And this means that from the second moment, we get this set of matrices, Fk star Fk, whereas what we want is the set of matrices Fk, which is the matrices that contain the spherical harmonic coefficients. So again, we want these matrices because they define or determine the protein structure, but what we get is Fk star Fk. So that's the result for cryo-EM. And this in turn implies that from the second moment in cryo-EM, the second moment determines the matrices Fk, or the 3D structure in this case, up to the action of the ambiguity group, which is the product of these k+1 unitary matrices. And in this case, I should say that this result was actually derived more than 40 years ago by Tzvi. And everything I showed you in some sense can be viewed just as a generalization and abstraction of the result of Tzvi from 40 years ago. Any questions? Everyone is afraid from the YouTube recording. Okay. So up to now, we focus on the second moment, and we understand the second moment determines the signal up to the action of the unitary matrices. But the question is whether we can identify classes of signals that can be recovered from the second moment. And to this end, we're going to use semi-algebraic priors. This part is based on joint work with Nadav Dim and Dan Edidin and Arun Suresh. So just to remind you, semi-algebraic prior, a semi-algebraic set M in Rn is basically, it's a very general definition, but generally you can think about just as a finite union of sets, which are defined by polynomial equalities or inequalities. And it includes some very important prior set signal processing. For example, it includes linear priors, the assumption the signal lies in or resides in some subspace, which is, for example, what we assume in PCA. It includes sparse priors, the assumption that the signal can be approximated using only a few coefficients in a specific basis. Again, a very popular prior. And it also includes some kind of a deep generative model, or at least an archetype of generative models of this form, where Z lies in some low-dimensional latent space. The A's are going to be the different affine transformations, and the etas are activation functions such as realm. So the assumption that F is in the image of this kind of network is also a semi-algebraic problem. Okay, so in this work with Dan, Nadav, and Arun, we derived very general conditions under which translation and semi-algebraic set are transverse to each other. Okay, so in some sense, we have the orbit of possible solutions that we get from the second moment, and the question is about the intersection of this orbit with the semi-algebraic prior. So we derived bounds for this problem. And this in turn implies that under these conditions, we can recover the signal uniquely from the second moment if it lies in the semi-algebraic prior with the proper dimension. So I'm not going to show you the specific result because it's very technical and quite messy, but I do want to show you some of the consequences. So for example, for phase retrieval, we got the following result. So we consider the phase retrieval problem of recovering signal F from its power spectrum, and we have a semi-algebraic set of dimension M. So if M is smaller than n/2, then a generic vector is in the semi-algebraic set is determined from the power spectrum. And if it's more than n/4, then any vector in a generic semi-algebraic set is recovered from the power spectrum. Okay, so I want to say this result is a bit informal. The specific result is a bit more technical, and there are some more details, but that's the main message of the results for phase retrieval. And again, it's important because this case includes linearity, sparsity, and deep generative models. We derived a similar result for cryo-EM. So now we have the cryo-EM, the same model that I showed you before, and with this representation. And R, the number of copies, should be large enough. And in this case, again, M is the dimension of this semi-algebraic set. And if M is smaller, more or less than 2n/3, where n is the dimension of the representation, then we can recover a generic F from a generic semi-algebraic set from the second moment. And if it's more than n/3, then every F can be recovered in a generic semi-algebraic set. And in cryo-EM, it also implies, if we think about sample complexity from the information theoretic perspective, it means that all these signals, if the signal lies in a sufficiently low-dimensional semi-algebraic set, then we can recover from the second moment, which in turn implies that we need only sigma to the 4 observations to recover it. So we need way fewer observations for recovery than what we need for generic, say, protein structures. Questions? Okay. So the next part of the talk is going to be about algorithms and how we can use algorithms which are currently used in phase retrieval to recover for cryo-EM and other problems. So this work is based on the joint work with Juho, Joe Khalil, Oscar Mikeren, and Amit Zinker. And to explain the idea, let's go back to the crystallographic phase retrieval problem. So the crystallographic phase retrieval problem is the computational problem in the heart of X-ray crystallography. And the problem is to recover a sparse signal from its power spectrum. It's a very important problem in physics and in crystallography. And a very useful way to think about this problem is to try to find the vector F, which is in the intersection of the two sets A and B. So we're looking for a vector or signal F in the intersection of two sets, where A in this case is all the signals with the measured data, all the infinitely many signals with the same power spectrum, and B is going to be the set of all sparse signals. Let's say we have some fixed sparsity level S, so all the signals which are S sparse. And we want to find a vector which is both with the measured power spectrum and is sparse enough. Now we can define projection operators onto the sets that we can actually compute efficiently. So the first one, which is PA of F, projects onto the set A. So it takes some current estimate of the signal, and basically it keeps the current Fourier phases and plug in the measured Fourier magnitudes. So this is the projection operator into A, and the projection into B is very simple. We just keep the largest S entries of F and just zero out the rest of them. So we have two projection operators, and then a very natural thing to do is to apply them iteratively, to start from some initial guess, and then to apply PA, PB, PA, PB, and so on. So this is called the Van Neumann's algorithm or alternative projection. It has different names. The main problem with that is that it doesn't really work. It stagnates very quickly, and this is something that people in physics know very well. So, and luckily they are very clever guys. So they actually they use these two main ingredients, and they found different algorithms different ways to use these two ingredients in a much more sophisticated way. And there are many, many different algorithms. It's called RR, RAAR, difference maps, HIO, and more. So for example, I like to use an algorithm called relaxed reflect reflect, RR, because we know that at least if there is no noise, there is no local minima. It stops only when it finds a solution, when it finds signal in intersection. The problem is that the running time may be exponential. It seems to be exponential, but as far as I know, there is no polynomial time algorithm for this problem. So that's the best we have. So okay, so this is for crystallographic phase retrieval problem, and if you want to generalize it to the MRA model that I showed you, it's actually quite simple. So the idea is as follows. So in the MRA case, from the second moment, we get this set of matrices, Fk star Fk, and we want the Fks. So this means that from the data, if we factorize this inner product, we get the Fks, but up to a unitary matrix, right? So given some candidates, say we factorize, we have some candidate signal, Ft k. So the projection into all the signal with the same second moment basically involves solving this problem, finding the best unitary matrix that matches the current estimate and what we factorized from the data. So basically, we want to solve this linear problem over the set of unitary matrices, which is it's a known problem. It's called the Procrustes problems, and basically it can be solved using SVD. So this data projection, it entails just an SVD. And the second algorithm, for example, sparsity, it's the same for phase retrieval and, for example, for cryo-EM. So we applied this algorithm to cryo-EM, where I showed you how we did the second moment projection, and the sparsity, we assume sparsity in the wavelet domain, which seems to be a good, a reasonable assumption in practice. And we run this algorithm, and importantly, it requires only sigma to the 4 observations. So we need only fewer observations than what people usually use. And it actually worked quite well on simulated data. So here you can see two proteins, these two guys, and this is just a Shepard phantom in green. The purple is the band limit approximation. So as I told you, we assume that the signal is band limited. So in purple, basically the best we can do is to recover the purple ones, because that's what we assume on the signal, and that's what we got quite efficiently. And again, we used only relatively few observations for recovery in this case. And that's it. So just to summarize, and in a few words about possible future work. So we've shown that semi-algebraic priors can be used to improve the sample complexity. Currently, we are interested in understanding, so we showed only results of uniqueness, the intersection between the semi-algebraic priors and the orbits. The question whether there is some kind of stability, for example, some kind of Lifshitz property, so that in practice, when we have some noise, we still can recover the signal stably with sigma to the 4 observations. So that's something we want to show. I showed you how we generalize classical phase retrieval algorithm to cryo-EM, and there are many extensions that we need to consider, encoding additional priors, and especially data-driven priors, which are very popular and useful these days, including, we assume, uniform distribution. So can we incorporate other distributions over the group and other modalities? And finally, something else that we were interested in understanding is about computational statistical gaps, and specifically whether there is the question whether, even if theoretically we can recover the signal to the four observations, whether we can find an efficient, computationally efficient algorithm that actually works with only signal to the four observations. We conjecture that the answer is no, but we don't know how to prove that. So that's another, I think, very interesting problem to consider. And that's it. These are the papers that I described in this talk, and that's it. Thank you very much for your attention. And I'll be happy to answer a few questions if you have.
Great. Let's thank the speaker by clicking buttons. I'll stop the recording here.